I am going to actually time this one so it doesn't hard stop like it has in the past. So we're doing Unit X and we're talking about a quiz. Much of this quiz will be this memorization that's required. Hopefully you recognize many of these elements already. The diatomics, I hope, are becoming more clear when you use H2, O2, N2, and when they can be part of a larger compound like NaHCO3, where H is just one there and oxygen would be three. But so these are elements that you'll need to know to move on to AP things if that's of interest to you. And regardless, I need to cover myself and prove that I showed it to you at some point. So radon, that's important. That's in basements. You should have your basement tested for that if you have a basement. Anyway, my suggestion is you take the ones that are weird, like potassium, sodium, mercury, lead. These are ones that really don't make sense, and you should put those in a separate pile and study those. You should study the diatomics together. You should try to couple these things in that fashion when you're studying. All right, so the organic alkanes, I'm really stressing that you know the prefix with the number of carbons. So meth is 1 carbon, F is 2 carbons, prop is 3 carbons, but is 4 carbons, pent is 5, hex is 6, and that's where I stopped it. I brought up octane in class being gasoline, so you should know that octane is 8, but that's not going to be asked on the quiz. Compounds. So again, when you're coupling things, this would be a good grouping for you to have for memorization. Right, so the compounds here, nitrous oxide, we talked about that, about how that goes in gas tanks to give more oxygen than air has. Ozone, O3, hopefully that makes some sense to you. Ammonia, NH3, carbon monoxide, hydrogen peroxide. One thing to notice that's sort of a pain here is that nitrogen dioxide, NO2, and nitrite, NO2 minus 1, are very similar, the difference being the one extra electron on nitrite. And I think I drew that on board, Lewis structure for most of you, so you could see the difference. This is more stable because nitrogen has a full octet, and this nitrogen only had 7 electrons on it. NO3, so I would put all these polyatomics, just study those for a couple minutes, put all the compounds together, study those for a couple minutes, and by putting them in these groups, you should memorize things a little better. So now today we did what I thought was more exciting, this energy and reactions. And we discussed how all reactions will require some activation energy. And in the instance of the balloon filled with hydrogen and oxygen that we showed a video of where it blows up quite loudly, there was the activation energy of having the candle light that balloon, and then the energy it released because this hydrogen and oxygen had all that energy stored and becomes water, thus going down. So the overall energy change would mean that the energy of the gas goes down lower to the water. What we really hoped to get out of all this, though, was a better understanding of the term exothermic. So exothermic reactions release energy, so the reactants would have higher potential energy than the products. An endothermic reaction would require energy. So if this were the reactants, the products, because it would require energy, would be higher. So products would be higher energy than reactants in that case. But in the case here shown, this is an exothermic reaction because the products being water has a lower energy than the reactants. All right, and then we discussed as sort of an entry into stoichiometry, well, if 2 moles of water give you 572 kilojoules, how much would 1 mole of water give? And it would make sense that that would be half of 572. And so that is 486. No, 286, my bad. 286. come from 1 mole of water, because if you cut this in half, then the energy you cut would be in half. And if you had 4 moles of hydrogen, all the oxygen that you needed, but 4 moles of hydrogen, then it would make sense that you would double your production of energy. So this would be twice as big. And so in that case, 1144, right? I think 1144 kilojoules. So, and then in the reverse reaction, if the gases combine and release as much energy, then it's going to take that much energy to get 2 moles of water back to the gases. And if we only needed 1 mole of hydrogen instead of 2, it makes sense that we would use half as much energy to make 1 mole versus 2 moles of hydrogen. So here were more problems. We watched the video of Bugs Bunny, which as a kid was how I was able to learn about science. Nitroglycerin breaks down into its component gases, and that's why it's so explosive and so such a shock hazard that it'll go to these gases in the blink of an eye. So if we balance the equation, we did that in class. If you have 4 of these, you won't be asked to do this on the quiz. This was just good practice. Where do you expect to find the energy? So would the energy be a reactant or a product? This is important. Because this is an explosive, we would expect the energy to be a product. And as a product, that would mean that this is an exothermic reaction because energy is released. And here you see it's 22,880 kilojoules for 4 moles. So if it's that much for 4 moles, how many kilojoules would there be in 1 mole? So if you consider 4 moles to be like 4 sticks of dynamite, if we had 1 stick of dynamite, then it would make sense that we would get 1/4 as much energy out of that. So 1 mole of nitroglycerin would give us 1/4, or what's that, 5720 kilojoules of energy in 1 mole versus 4 moles. And if we drew the energy diagram for this, this would be, the nitroglycerin would be of higher energy to start, because as with the egg that I dropped on the counter, this has all of the stored energy, and it's because of the stored energy that the explosion happens when you go to this. This was similar to what we did with the hot hand warmers. The hand warmer that I handed you at the beginning of class was this gel that had all the stored energy in it. It released that heat as you cracked the pin. That cracking of the coin was the activation energy, and then it released all that energy to heat up. So this is exothermic. The reaction we did with the hand warmers was exothermic. And yes, so this is what an energy diagram would look like for that. If you want to see an endothermic one, here's ozone. How you make ozone. Ozone happens through energy coming in the atmosphere. Lightning or something will make ozone from oxygen. So oxygen needs to go up to make ozone. You need to put energy in, and it turns out that it's 286 kilojoules to get from here to there. And if we had 1 mole of ozone instead of 2, how much energy do you think would take? It should hopefully make sense to you that it'll take half as much energy to get 1 mole of ozone. If it takes this much energy, 286, to get 2 moles, it would take half that much, or 143 kilojoules to make 1 mole. And that's that. So let me know if there's anything else you need. You send an email or whatever, but hopefully that'll get you through the quiz.